Hello! In this video, we'll be talking about memory mapped input and output. So, under memory mapped input and output, we control peripherals by reading or writing memory locations that are called registers. This is a little bit misleading term. They're not necessarily a bank of flip-flops, but they're someplace in memory where by, say, writing to that memory location, we can cause physical things to happen in the real world, and by reading, we could measure the state of the real world. So part of the address space in our processor is reserved for I/O registers rather than for program or data. And in C, we use pointers to specify such addresses to read or write. Here's an example of the memory map of the FE310. We see around address 1000 through 1FFF is boot ROM, and I'm just calling that 1000 for convenience, even though it's obviously a longer number. So when the processor starts, it begins fetching instructions out of that ROM, and the first thing it does is jump to the one-time programmable ROM. That, in turn, soon jumps into the code flash, so the program is stored in flash memory and is in these addresses. I'll call that 2 million through almost 4 million. There's also static RAM, starting at this location. Call that 8 million. And then there are a bunch of peripherals, and they are at different addresses in memory. Spanning this range. And we'll look at several of those peripherals in this chapter. So let's jump in with an example of memory mapped I/O in C. We'll start by including stdint so that we can define our integers of various sizes. And the registers are 32-bit registers, so let's use the unsigned integer 32 type to represent a 32-bit number. Let's say we want to use two registers. One is an input value for general purpose I/O, and one is an output value. And we'll talk later about exactly what this means. These registers have 32 bits in them that can tell you the value of an I/O pin, or drive a value out to the pin for the input and the output registers. We saw that the GPIO is in this memory location starting at 1001 2000, 1001 2000, and the input registers at exactly that address. The GPIO output value is 12 bytes later. So let's declare pointers to these addresses so we can read and write what's at the address. They are a pointer to an unsigned int 32, and we'll declare them as volatile, which tells C that the value might be changing outside of the program's control, and that anytime we want to look at that value, we actually need to go out to the memory map and fetch what's from there, rather than assuming that it was the same as the last time we fetched it. So if we wanted to read the value of all 32 GPIOs, we could take that pointer to the input register, dereference it, and that will give us a 32-bit number, and we just put it in a register, put it in a variable. Suppose in particular we wanted to know the value of bit 19 of the GPIO. So of that 32-bit register, we need to extract bit 19. We can do that by first getting the entire 32 bits, then we can shift it right by 19, and AND it with a 1. And that will leave us either a 0 or a 1 with the value of the 19th bit of GPIO. Let's say we wanted to wait for that bit to become 0. We could have a while loop. Inside this while loop, we're looking at the value of the bit. As long as it's 1, this value is 1, and the while loop is true. So we wait until it's no longer 1, and now the bit is 0. Similarly, if we wanted to wait for bit 19 to be 1, we could put a not before this. So while the value was 0, we wait. Once it becomes 1, we stop waiting. If we wanted to write a 1 to a particular bit, let's say bit 5, we could take a 1, shift it left by 5, so now we have a 1 in column 5 and zeros everywhere else, and OR it with the existing value of the register, and that will put a 1 into the 5th bit and leave all the other bits unchanged. Similarly, if we wanted to force the 5th bit to be 0, we could take a 1, move it left by 5 into the 5th column, and then NOT it. And now we're left with 1s in every column except the 5th bit, a 0 in the 5th bit. If we AND that with the value of the GPIO register, then we will leave anything AND 1 is itself, anything AND 0 is 0. So we'll leave all the bits the same, except bit 5, which will be forced to 0. Let's take a look at that in a little more detail. So let's say we wanted to read the value of the 3rd bit of a particular register. So we have the pointer of the register, we dereference that pointer, and we come out with this 32-bit value. If we then shift it left by 3, bit 3 goes into the bottom position, the other bits move over, and we're left with zeros in the top. Then if we AND that with the number 1, a 1 is a 1 in the least significant bit and zeros everywhere else. So B3 and 1 gives us B3. All the other bits are 0. So it leaves us with a 32-bit number that's either 0 or 1, corresponding to the 3rd bit of the register. As another example, if we wanted to write the bit to 1, let's start with a 1. We'll shift it left by 3, so now there's a 1 in the 3rd column and zeros everywhere else. Then we'll read the value of the register, gives us our 32-bit value. We'll OR it with the 1 in the 3rd column. So 0 or anything is itself. That leaves all the other bits of B. But 1 or something is 1, so we force a 1 into the 3rd column. And we've changed the IO register to now have a 1 in the 3rd column and a 0 everywhere else. Finally, if we want to write a 0 to a particular bit, let's start with our 1, shift it left by 3, now that's a 1 in the 3rd column. Now we invert that, so we've got zeros in all the columns except that 1 in the 3rd column. Now if we AND with the value of B, 1 and anything makes itself, 0 and anything makes 0. So we're left with all the bits of B unchanged except the 3rd bit is forced to 0.